Hi, in this video, let's take a look at some various access options for wide area networks. And there's a lot of them. So I'm going to go through all this in a single video. This is just an introduction into each. Some of these we'll look at in a little bit more detail in later videos. Okay, so in the old days, back when I was young, we used the public switch telephone network for just about most of our networking, at least a lot of our remote access to the network and to the servers and mainframes. So a lot of this involved modems to convert or translate the digital signal coming from the computer to the analog signal that had to be sent over the local loop to the public switch network. Once in the public switch telephone network, the PSTN, a lot of that was all then digitized using T1 circuits. And we'll talk a little bit more about T1s coming up here in just a moment. But what the modem did was it modulated the binary or the digital signal into an analog signal and then demodulated it coming back in from the local loop back into the computer there on the left and a router there on the right. So as far as the bandwidth, it was relatively slow. It was a theoretical maximum of 56K, closer to 53K. We tried to do some other things to kind of speed that up, but it was slow, very slow, at least by today's standards. Okay, but we still, dial-up WAN is still a possible option when no other wide area network technology is available. You might require it if you're in a remote location and you really have no other options. But you got to realize it's going to have to be low bandwidth and not sending. You're not going to be able to do video on over it, and so it's going to be relatively. It's going to be slow. But during the, I always like to mention this. During the 2011 protests in Egypt, after the Egyptian government actually shut down access to the internet throughout all of Egypt, there was an activist group called We Rebuild that actually used dial-up modems and connected to the internet through servers in Sweden. And then they created a wiki page to help others figure out how to do this and how to access different parts of the internet and get information and things like that. So very ingenious. So when all else fails, and if you still have a telephone connection, there are still places out there you can actually connect to the internet via a dial-up modem. Okay, kind of the next, as I've talked about this in a previous video, but kind of the evolution going from public switch telephone network and dial-up modem, still using the public switch telephone network, but was using something called ISDN, which is also a legacy technology, and I haven't seen it out there in many years. I'm sure that it's impossible to get in the United States anymore. But what it wanted to solve was the problem with the slower digital analog modems. And ISDN still used the local loop and the public switch telephone network because the public switch telephone network was a digital carrier by this time. And used T1 links, which we're going to look at in a moment. You could actually get almost 100, you get 128K to almost 1.544 megabits using ISDN. We'll see that in a moment, but using the public switch telephone network, which comprised of a digital hierarchy system that used time division multiplexing, based on T1 lines. We'll look at that in a moment. You could actually get, and again, anywhere from about 128K to 1.544 megabits. You connected to the ISDN. I remember when I had my ISDN connection to Tandem computers. I had something called a terminal adapter, and there's also something else that was used called an NT1. Not important, but you had to have a device or two to actually connect from your home to the other end, and it all had to be over ISDN, and you're paying for this, or in my case, my company was paying for this service. So it was all pre-set up with the phone company. Okay, so a little bit more on ISDN, and we'll see this with T1 too, but it used something called bearer channels. So you can see PRI up here. So we got this BRI, basic rate interface, and PRI, primary rate interface. So the total bandwidth of this of BRI was 144K, really 128K of data. So this is what could actually carry the data. For PRI, it used 23 64K channels. So 23 bearer channels of 64K each. So it was just under 1.544 megabits. T1 was the standard in the US and Canada. E1 was the standard in Europe. There's also a J1 standard in Japan. But we'll also talk about this a little bit when we get into T1 and time division multiplexing. But we also had D channels, which carried the out-of-band signaling. So I mentioned there were two types of ISDN interfaces: BRI, basic rate interface, which gave you about 128 K BPS, 128,000 bits per second of data. And there's also primary rate interface, which was almost a T1 line, almost 1.544 megabits per second. All right, ISDN, I've mentioned this before. Sometimes people called it I still don't know, or it still does nothing. So anyway, it's kind of the cynical attitude some people unfortunately have towards their providers. But ISDN was also used as a way of backup to other tech provider circuits. Like if you're using frame relay, you might use ISDN as a backup if your frame relay or dedicated circuit went down. You see up above there a T1 frame. I'm going to talk more about that in just a moment. But ISDN has gone away, and that's because all people could connect at much easier, cheaper, and at much higher bandwidth using things like DSL and other broadband services. So ISDN is a thing of the past. Okay, let's talk a little bit about point-to-point lines, which or sometimes known as leased lines. So these are quite common still today to connect between two sites. Been around for a long time, also called leased circuits, serial lines, serial links, point-to-point links, T1 links, E1 links, whatever you want to call them. We can see here that you connected through a CSU DSU that connected your network to the service provider's network. The bandwidth, the price for these lease lines depended upon the bandwidth that you were getting and the distance between the two paths. And we can see that this could be actually quite costly. I've mentioned this before. Just place I once worked, we had actually multiple T1 connections to our internet service provider, and we were paying about almost $1,500 a month per T1 connection. So especially now, a lot less expensive, and actually we'll see that there's a lot better options than T1. So T1 comes from a technology known as time division multiplexing. And we're going to take a look at this is where our digital hierarchy actually comes from, starting with T1s. So in this hierarchy, what it is time division multiplexing is a communications process that transmits multiple digital channels known as DS0 channels. You can see these here. Each one of these is a DS0 channel that can send 64 kilobits per second of information. And that's because that's what was required to carry a telephone call. So the phone company created a way that they could actually multiplex, send multiple 24 channels, 24 voice conversations digitally at the same time over a single circuit. So T1s are really a DS1 because it's part of what's known as a digital services hierarchy. Let's see. So this is what I wanted to get to here. So a T1 had an actual signaling rate of 1.544 megabits per second. T1, or we call it, or DS1, but we call them T1 links. The service was known as DS1. Now, what was actually sent was, it was 8 bits per channel. So you had 8 bits per channel in these 24 channels, but for each frame consists of channels of 8 bits each, not 64K, but the frames were sent at 8,000 frames per second. So 8 bits per channel at 8,000 really frames per second gave us 64,000 bits per second. Or let me say that again, 8 bits per channel at 8,000 channels per second. So looking at it as from a single channel perspective, you got 64,000 bits per second. The DS1 frame was 8 bits per channel, 24 channels at 8. So you sent those frames at 8,000 frames per second. That's where we got the 1.544 megabits per second. Okay. So this kind of shows you the North American and European or international standards, digital hierarchy standards. Slightly different, has to do with the number of these DS0 channels. So you can see that we have DS0, DS1, DS3. So you might hear the term T3s. That's a DS3, usually sent over coax cable. And you get 45 megabits per second, almost 45 megabits per second. And then when you start getting into fiber optics, that's when we get into these optical carriers, something called SONET. We'll talk about that in a moment. And start getting into the gigabits, even the terabits now. Okay, and again, but it really all comes from this hierarchy. It really comes from being able to send a single channel 64 kilobits per second channel for a voice call. And then you can use, let me kind of back up here because it is kind of interesting here. So when you had what would happen a lot of times is that your telecom provider would bring a T1 circuit. Say we have the central office here and your company here, or just say headquarters here, maybe bring in a T1 circuit, and then you would pay for how much of this do you want? How many of these DS0 channels do you want? And if you're just paying for part of it, let's say 6 of these, this would be known as a fragmented T1 link. Okay, and you can actually see that this is where we got the whole idea of ISDN, a BRI would use this between you and the provider, and then also carry these 2 channels from one end to the other. You had 2 DS0 channels. If you bought a PRI, you'd actually get you'd get 23 channels, and then it used some other stuff for framing. All right. Anyway, I used to talk a lot about this stuff when I taught a class on data communications. Oh my gosh, that was a long time, back in the 1980s and 1990s. All right, let's continue. We've got a lot to talk about here. So So point-to-point circuits, if you want to have all these different leased lines, I talked about this in an earlier video, you could do these full mesh link connections, okay? But you can see that this is requiring a lot of links between everybody. If you want everybody to talk to everybody, we're talking about a lot of connections. Matter of fact, there's the formula there on the right. And it's the number of nodes minus 1 times the number of nodes divided by 2. And that can be quite costly, okay, because you're paying for all those leased lines, okay? So what if there was just some way we could have some kind of provider that we just all connected to and let this provider look like almost a virtual switch to us, okay? And by the way, eventually, we're not there yet. I mean, we're there today, but not in this presentation. Metro Ethernet does this. We actually connect to kind of a virtual switch in a way, which is Metro Ethernet. Okay, but let's continue along the path of what kind of came after ISDN and these lease lines. Technology I introduced earlier talked about frame relay, which is an NBMA, non-broadcast multi-access wide area network technology. Now, frame relay doesn't actually, there we go. Frame relay doesn't actually specify, the standard doesn't specify how the information is transmitted within the frame relay cloud. What they talk about, the standard talks about is how you access the frame relay provider's cloud. It's up to the provider to determine how they were going to do all these, what we call virtual circuits. We'll talk about them in a moment. And you could have a full mesh of virtual circuits, but that's quite costly because, again, you're paying for each circuit. You're paying the provider for each circuit. Or you could do a hub and spoke topology where everybody communicates with a single node. So continuing with this, so non-broadcast part of it means that frame relay does not use broadcast. So there is no broadcast capability. Frame relay is a legacy technology and has been replaced by other broadband technologies, including Metro Ethernet. Okay, so one of the problems with having a full mesh is, guess what? You're paying, first of all, you're paying for the access circuit, which is typically, you know, your provider isn't going to do that for you, and you usually have to go through a separate provider maybe to get, but it's really just the access circuit is how you access the provider's network, the provider's frame relay network. So that's one cost. And then you're having to pay for each circuit. So the frame relay provider will actually set up, of course this is their job, these PVCs, these permanent virtual circuits for you. They'll ask you, who do you want connected to who? Which node do you want connected to what node? You can have them all interconnected in a full mesh, or what I'm showing here, a hub and spoke. Of course, the fewer circuits you have, the fewer virtual circuits you have, the cheaper it's going to be. Okay. And again, the standard does not specify how this is done inside the frame relay cloud. Matter of fact, back in the old days, a lot of frame relay providers used ATM inside the frame relay cloud. We'll talk about ATM in a little bit, in just a moment. Okay. All right. So in this case here, instead of full mesh, we have everybody is connected to HQ. Everybody has a permanent virtual circuit between the branch and HQ. So if we need branch 1 to talk to branch 2, it's got to go through HQ. So the branches are known as spokes, and HQ is known as the hub. Okay, so frame relay, data rates weren't anything to write home about. They were okay at the time, but we're talking around 4 megabits maximum. Commonly, you'd be talking 64K, 128K in a lot of cases. The PVCs were uniquely identified with something known as a DELC, Data Link Connection Identifier. We used to spend a lot of time talking about frame relay and CCNA, CCNP, and even CCIE, but fortunately, we're kind of moving away from it. But it's good to kind of see the evolution of all this. Speaking of legacy technologies, I'm going to spend a lot of time on this, but was ATM, asynchronous transfer mode. It was built on using these small cells, 53-byte cells, fixed length cells. So they thought if they were small and fixed length, that the service provider network could actually move traffic around fairly quickly. But actually, it was good for some things. ATM cells contained a 5-byte ATM header followed by 48 bytes of the actual data, the actual payload. They were well suited for voice and video at the time, but there's better solutions today. They required a lot more overhead because you had so many cells that you were sending. And again, this was a kind of like, well, it was like frame relay in that the provider would set up these virtual circuits in their ATM cloud between the endpoints. Okay, let's move away from that old stuff. Now what we're getting into nowadays is stuff called Metropolitan Area Ethernet, also known as Ethernet MAN or Metro Ethernet. So inside the provider's cloud, there's a lot of fiber optic that's there. So most of this is all done over fiber within the service provider's cloud. How they actually do it in the cloud is up to the provider themselves. But as far as the connecting to the Metro Ethernet cloud, it looks just like Ethernet. So it's a technology that is already known by the people connecting to the cloud. So you have reduced expensive administration. It's a known technology. It's also cheaper than SONET and SDH, which I'll talk about here in a moment. So it's very easy integration with existing networks. So a typical provider's network, I got this from Juniper Networks. I really kind of like this. It shows how you can subscribe down there at the bottom, LTE, 4G, 3G, 2G, even 5G, or via wireless or wired cables, and inside the network themselves, how they actually carry it. Could be carrier Ethernet or Ethernet VPNs and all kinds of stuff, and then just showing the edge and core routers and multi-layer switches. But and as far as their topology, it could be ring, hub spoke, full or partial mesh. Okay, so again, this is what it has been and is replacing frame relay and ATM. You can't. I think Verizon ended their ATM probably about 15 years ago. I know AT&T ended their frame relay probably, again, at least 10 years ago, if not longer. So and ISDN hasn't been available for a long time. So this was one of the options that we have. Let's look at a couple of something else that before we end this presentation. I want to talk a little bit about SD-WAN, software-defined networking. This is software-defined networking in a wide area network. So this is a big thing that's happening. Managing all this WAN from both the perspective of the provider and the user is quite cumbersome. So SD-WAN is a way that we're using software to help us manage the operation of the WAN. It decouples the hardware from the control mechanism. Basically, what that means is we're using software to make the decisions for us instead of configuring each of the pieces of hardware separately and with a lot of configuration commands. And this, we're using software to really control and manage all this. So the effect that they're trying to get with all this is to optimize the bandwidth. To help direct traffic along the best path from the branch offices to the data center sites. So you're going to be hearing a lot more about SD-WAN in the near future. Okay, so before we end this presentation, just a few things, a lot to consider on the various WAN access options we looked at. What is the purpose? How do you want to connect? Will the enterprise connect local branches in the same city area, connect remote branches, connect to a single branch? So what is it going to look like? What are you connecting? Will the WAN be used to connect internal or external employees or customers? So is this just to connect internal devices, or do you need remote devices to be able to connect as well? What is the geographic scope? Is it regional? Is it local, regional, global? Is this a WAN one-to-one single branch, or one-to-many, or distributed? What are these connections going to look like? What's available in all these different areas? What are the traffic requirements? What type of traffic must be supported? What are the quality and performance requirements? Do we want quality of service? Do we want to be able to prioritize certain kinds of traffic? Should the WAN use a private or public infrastructure? Private infrastructure, okay, that's going to offer us some security. Public internet infrastructure, not as secure, but more flexible and lower ongoing expenses. We're going to talk about VPNs and the internal infrastructures in just a moment, in later videos, I should say. So for the private WAN, should be dedicated or switched. For public WAN, what type of VPN do we need? Which connection options are available locally? Okay. What are the costs of those connections? So there's a lot to think about, a lot to look at. And this is one of the reasons why, you might have various options, you might utilize various options. And this is why, SD-WAN is being looked at to help make these options at least a little bit more efficient on how we're actually forwarding the data over the various WAN infrastructures. You may be using more than one. You may be using Metro WAN for one. It might be multiple providers, multiple service providers, multiple different kinds of connections, VPN connections, etc. Especially if you're connecting different regions of the country or even across the world, you're gonna have to go through different providers and how you're gonna get everything all interconnected. Whew, a lot to think about. All right, we'll be continuing this series with more videos here shortly.